Hello everyone. So today I'm going to discuss about the structure activity relationships of benzodiazepines. So as you know, benzodiazepines are very important drugs. They are going to act on central nervous system. So they can be used as sedatives and hypnotics. Some of the benzodiazepines can be used as anticonvulsants, etc. So let us now talk about the structure activity relationship of benzodiazepines. Okay. So this is a basic structure, the general structure of the benzodiazepine. I have shown you the structure along with the numbering pattern. Okay. So benzodiazepines are fused ring heterocyclic compounds consisting of a benzene ring attached with 7-membered heterocyclic ring consisting of 2 nitrogens as heteroatoms. Okay. So I'll be discussing the structure activity relationships of benzodiazepines position wise. So there are totally 9 positions. So we will try to discuss the SAR of benzodiazepines starting with position number 1. Okay. So coming to the first position. So small alkyl groups, if you look at here, so small alkyl groups like methyl group have been substituted at position 1. And do remember, these methyl groups are very, very important as they can increase the lipophilicity. So you should understand, in order for a drug to have or for a drug to cross the blood-brain barrier, lipophilicity is one important parameter. Unless and until the drug is more lipophilic, it cannot cross your blood-brain barrier and it cannot reach the central nervous system, and therefore the biological activity cannot be expected. Okay, so the introduction of small alkyl groups can increase the lipophilicity, therefore it can cross the blood-brain barrier and it reaches the central nervous system to show its biological activity. So here I have shown you 2 important drugs. One is temazepam and diazepam. So in both the drugs, okay, you're having this methyl group here. Okay, at first position, it is occupied with a methyl group. Coming to the second position, the keto group is very essential for activity. Most of the benzodiazepines have this keto group at second position with one exceptional drug. What is that exceptional drug here? Chlordiazepoxide. Okay, so this drug is having methylamine group at second position instead of ketone group. So more than 90% of the benzodiazepines will have ketone group at second position, but with few exceptions like chlordiazepoxide, which has methyl amino group at second position. So this is a structure of your chlordiazepoxide. Okay. If you look at the structure of chlordiazepoxide, this is your second position, which is occupied with methyl amino group. Okay, now this chlordiazepoxide can undergo metabolism by a process known as oxidative deamination to produce demoxepam. What is happening here? Again, the methyl amino group NH CH3 has been converted into a ketone functionality. This compound, you can call it as demoxypam, which is the active metabolite of chlordiazepoxide. Okay. Next, coming to the third position, introduction of hydroxyl group, that is OH, at third position results in polarity. Very, very important. Okay, as a result, what happens? The drug is directly excreted in urine, hence short duration of action is observed. Okay, now if you are going to introduce a hydroxyl group, generally hydroxyl groups are hydrophilic in nature, so they can increase the water solubility of the drug. Okay, so because of this hydroxyl group at third position, it results in polarity. As a result, the drug is directly excreted in urine, hence short duration of action is observed. Okay, so the problem with short duration of action is you have to give repeated dosage of drugs to get the patient relief from the symptoms. Okay, so there are some drugs which have hydroxyl group at third position, like lorazepam, oxazepam, tinazepam. So I have abbreviated as LOT, L-O-T. So L stands for lorazepam, O stands for oxazepam, T stands for temazepam. So all the three drugs are polar drugs which contain OH group, and they are short-acting benzodiazepines. Look at the structures of these three compounds. So look at here. This is your third position, first, second, third. So at third position, there is an hydroxyl group. So because of the presence of hydroxyl group, these three drugs have very high polarity. Because of this high polarity, they can easily excrete out from the body, and therefore the duration of action of the drug also decreases. Okay, next, coming to the fourth position, all benzodiazepines are having unsaturation at fourth and fifth position. So saturation decreases the biological activity, right? So this is a general structure of benzodiazepine. You're having a double bond at fourth and fifth, which is very essential for the pharmacological activity. But if you are going to remove this double bond at fourth and fifth, the biological activity is going to decrease, or sometimes the biological activity may be abolished completely. Okay, so my dear friends, you should understand a double bond at fourth and fifth is essential to improve the biological activity of benzodiazepines. Next, coming to fifth position. So phenyl group at fifth position is essential for activity. If this phenyl group is substituted with electron withdrawing group at ortho or diortho position, it increases the activity. Okay, if electron withdrawing groups are substituted at para position, it decreases the activity. For example, you take diazepam. Okay, so I'm talking about this fifth position, right? At fifth position, introduction of this phenyl ring is very important for biological activity. So if this phenyl ring is substituted with electron withdrawing groups at ortho or diortho position, it can increase the biological activity. Okay, so this is diazepam, which is having phenyl group at fifth position. Lorazepam is also having phenyl group at fifth position. Okay, so next, flurazepam is also having a phenyl group which is attached with an electron negative group, that is fluorine, which is having very high electronegativity. And there is one advantage here. If you introduce fluorine to the phenyl group at fifth position of benzodiazepine ring, this fluorine can increase the lipophilicity. Okay, So if you increase the lipophilicity, definitely the drug can cross the blood-brain barrier and it reaches the central nervous system to show its biological activity. Similarly, look at the structure of clonazepam. It is having chlorine, which is attached to the fifth position of the phenyl ring. So even chlorine can also enhance the lipophilicity. It helps the drug to cross the blood-brain barrier and improves the biological activities. Okay. Next, coming to 6, 8, and 9th position. So these three positions should not be substituted. So 6th position, 8th position, 9th position. So I have highlighted with yellowish marker here. So these positions should not be substituted by any group. Okay, so better you can leave those groups unsubstituted so that the biological activity cannot be disturbed. Next, 7th position. So an electron withdrawing group is essential for activity. Like, for example, you take chlorine, nitro group, etc. So these electron withdrawing groups can increase the biological activity. So one more important point, potency depends upon the electronegativity of the group present at 7th position. Now, for example, if you take these two structures, diazepam and nitrazepam, I will say nitrazepam is more potent than diazepam. Why? Because there is a nitro group here and there is chlorine. When you compare the electronegativities of these two groups, nitro group is more electronegative. It is having combination of nitrogen and 2 oxygen atoms, whereas in diazepam it is only 1 chlorine. So definitely nitro group will have greater electronegativity profile. So as per the statement what I have given, the atom with highest electronegativity will have greater potency. So that's the reason I can tell you that nitrazepam is more potent than diazepam. Okay, so this is about your essay of benzodiazepines. Okay, thank you.